today students. So we are continuing our lesson. If you memorize Fleming right hand rule for electromagnetic induction, okay. So just to recall what we have done the other day. So we were talking about electromagnetic induction, that is production of electricity when there is a change in the magnetic field through a conductor. Okay, using a conductor, the conductor when undergoes a change of magnetic field, it will induce current in that conductor. Okay, that is for the straight wire where we use Fleming right hand rule. So do not confuse with Fleming left hand rule which you learned earlier. That is for motor, alright, for effect of force in the magnetic field. Okay, so today what we are going to do, we are going to continue for solenoid. So for solenoid, we have to use Lenz's law to determine the direction of induced current. So solenoid is basically a coil, a wire, okay, winded, right, in a cylindrical form. Okay, then you put in, push in a magnet into it, or you take it out. So you want to know what is the direction of current induced. Okay, for this Lenz's law, there's no choice, but you have to memorize the Lenz's law. Okay, so for Fleming right hand rule, they won't ask which finger is for what. Sometimes they do, but most of the time they don't. They will be more interested for you to apply the Fleming right hand rule to determine the direction of current. But for Lenz's law, sometimes they may ask what is Lenz's law. Okay, so you can refer page 74. Okay, in your notes, page 74, you can get this definition. That is, I'm going to use the definition of Lenz's law and then apply it how to determine the direction of current. So this diagram is in page 75, so you can see there. So that's what we are going to do today, to see the direction of induced current in a solenoid. Alright? Okay, so what is mentioned here? The direction of the induced current in a solenoid is such that its magnetic effect always opposes the change producing it. So what does it mean? What does they mean by this? Meaning, when the magnet pushes through this solenoid, alright, definitely there's a current induced because this solenoid conductor cutting the magnetic field, the magnetic field of this magnet. Okay, there's a magnetic field in this magnet. So this magnetic field is being cut. So when it is cutting the magnetic field, it will induce current. The direction of the induced current, remember earlier we learned, when there is a current in a solenoid, when you learn about right hand grip rule, remember the first lesson, when there's a current in a solenoid, there is a magnetic field following right hand grip rule, right? If there is a direction of current, straight in a straight wire like this, there is a magnetic field around it, or if there is a solenoid, this is a solenoid, so the direction of the pole on that solenoid will be north pole. Right? So please refer. So here, to explain the direction of current, you have to apply two things. Although one only I mentioned about Lenz's law, but you also have to apply the understanding of right hand grip rule over here. I repeat. Lenz's law must be applied together with right hand grip rule to determine the direction of current. Then only, okay, I don't want to write the right hand grip rule, then you might be confused. So, but I'm telling you now, because please remember that idea of right hand grip rule which is applied together with Lenz's law to tell you the direction of induced current in this solenoid. Okay, so what happens? When the magnet goes in, there is a current induced in this solenoid. The direction of current induced in this solenoid, remember when the current in a solenoid it induces a magnetic field, right? So that magnetic field will oppose the change producing it. What is producing it? North pole magnetic field producing the current. So this current that is induced will oppose the north pole. So what pole will oppose the north pole? Definitely a same pole will oppose the north pole. Okay, what is the same pole of north pole? Another north pole. That means the current that induced here. Before I write the direction of current, what I must do? North pole going in, current is going to induce, the induced current will produce north pole. You have to do this first, right? North going in, opposing the north will induce a north pole by that current. Okay? So if it is north pole here, now you apply your right hand grip rule. Okay? Your right hand grip rule says, if this is the north pole in a solenoid, so this is the direction of current. So, can we see now? So this is the north pole going, opposing, current induced oppose the north pole. So, the right hand grip rule will tell you the direction of current for this north pole is follow this way. That means, this is the direction of current. Simple as that. Okay? So if this current is going this way, as you can see, okay, so the direction of current is going to be like this. So your galvanometer will deflect, depend how you fix the polarity, either it will deflect this way or this way. This is a zero center galvanometer. Okay? So the needle can move either way. Alright? So it doesn't matter, you can draw any direction. Okay? So suppose the current going this way, so I draw it this way. You got it? So when north pole going in, the direction of induced current such that it will oppose the north pole, which producing it. Right? So that's the definition. So north pole going in. Suppose, okay, now I include this. Suppose I make it this as south. I make this as south. So your north pole of the magnet will be here. So when south pole goes in, what is the direction of induced current here will be? It will produce south pole to oppose the south. So here will be south. So when you draw south for south, which is going in, so the direction, now this is south. So again using solenoid, so this is north. So for south, if this is south, this will be the north. So the direction, because your thumbs only shows the north, right? So if this is south, this is north, so I draw. So the direction of current now changes. Alright, it becomes like this. Okay. So the current goes this way. So your needle will deflect now in this direction. Okay, so this is how Lenz law is applied. So when north pole goes in, and north pole is induced, in order for the north pole to induce, the direction of current must go. Okay, in this case, if this is the north, it will go anti-clockwise. In this case, this is south, so if you look from here, it is like clockwise. Okay, it depends where you look from, right? Most important, you must determine the pole of the induced current first before you tell the direction of current. Okay, the pole induced is south, so the direction of current here must be north, so you will go this way, opposing the south. Okay, now suppose the magnet is inside here. Alright, it's already pushing. Now the magnet is inside here. So now what you are doing, the north pole now is being pulled out, taking out the magnet. So again we apply the Lenz law. The direction of induced current in the solenoid is such that its magnetic effect always opposes the change producing it. Now there is a magnetic effect by this flux. Okay, this flux is the flux for north pole. So the north pole is now leaving. So when the north pole is leaving, to oppose the north pole from leaving, it must attract. So to attract, what is the pole should be induced here? It should induce the south pole. To attract back, yes? To attract back. Just now it oppose. And when north pole going in, oppose, south pole going in, oppose. When the north pole is leaving, or south pole is leaving, this solenoid induced magnetic field will oppose the magnet from leaving. Leaving means it must, opposing means must attract back. So when north is leaving, it has to attract back. So to attract back, it must produce a south pole. So for south pole again, this is south. So the direction of induced current will be this way. So I apply the right hand grip rule, right? So here is south pole because south is leaving and north is leaving, so it must induce a south pole. Suppose this become south pole, so this become north pole. Now the south pole is leaving. Let's say I put the south pole like here. Again, now I'm pulling out the south pole. So when I pull out the south pole, of course the magnetic field for south pole is this way. Just normal ignoring. Okay, so when the south pole is leaving, what is the magnetic field effect producing inside it to oppose? South is leaving, so it must produce a north pole in it. So for north, this is the north, right? So you use the right hand grip rule. So the direction of induced current will be this way. Of course, it becomes this way. Alright? So this is how the Lenz law works. That's why I said it's a bit abstract. So for Lenz law, is remember, direction of induced current is explained by Fleming right-hand rule and Lenz law. Fleming right-hand rule is applied for straight wire, which we discussed in the last class. For solenoid, it's explained by Lenz law. But Lenz law is not simple because there are 4 situations: north going in, north coming out; south going in, south coming out. So each time each pole goes in, the direction of current induced will oppose the magnetic effect which is producing it. Oppose. So here the magnetic effect which is producing it, south pole, and the south pole is going in. So when the south pole goes in, you must induce a south pole. The magnetic effect, induced current magnetic effect will oppose the south. So it must produce south. So write south first. Then you use your right hand grip rule to tell the direction. So you please go through the notes. They explain in page 74 and 75 very well. Okay, this is in 75 about the direction of induced current. Okay, so that is all about the direction of induced current for straight wire and solenoid, which is using 2 different ideas to determine the direction of current. One, for straight wire we use Fleming right hand rule. For solenoid we use Lenz law. So memorize the Lenz law, no choice, and then you must use together with right hand grip rule for the Lenz law to determine the direction. Okay, so let's see. Okay, the second part. Okay, the currents are induced. How strong the current going to be get induced? The magnitude of current. So the magnitude of current is explained by Faraday law. Alright? It's in page 76. So Faraday law, what does the Faraday law says? Faraday law says, right, the magnitude of induced current is directly proportional to the rate of change of flux. Okay, so you can look at page 76. Then we split up the statement. Okay, Faraday law. The size of induced EMF is directly proportional to the rate at which the conductor cuts through the magnetic field lines. That means how fast the rate of change of flux. That means if we can push very fast into it, the rate of cutting flux is increased. That's one way. Right? That's one way. So Faraday law tells you the magnitude, whereas the direction it tells by the induced. The direction is for Lenz law and Fleming right hand rule. So 2 different settings, and this is for direction, this is for magnet. So I have to repeatedly tell because most of the time students confuse with the Lenz law and Faraday law. Remember, Lenz law for direction of induced current in solenoid. Faraday law is the magnitude of induced current. Alright, it can be a straight wire, it can be a solenoid, doesn't matter. Okay, so what is the magnitude of induced current? So it is that I write a statement, maybe to reinforce. Okay, what does the statement say? Okay, the size. The size, remember the size, magnitude. Okay, of the induced EMF. EMF or current, electromotive force or current is the same. Is directly proportional to the rate. Look at the rate. That means how fast, at which the conductor cuts through. How fast it's cutting? Cuts through the magnetic field lines. Okay, so that is the general statement. Okay, so we can expand this. The rate of cutting of flux can be increased by 3 methods. One, you use speed, very fast you cut. Okay, one, you use the speed. The faster you move and the faster you take up, bigger the magnitude. Number 2, of course, the rate of cutting. If you use stronger magnet, that means you have more flux. If you use stronger magnet, more flux. So more flux, more rate of cutting. So number 2 is strength of magnetic field, B. Number 1, speed. Number 2, the strength of magnet that you are using. Okay, and number 3, of course, if you are using 5 turnings, now you change it to 20 turns. More turns when you cut, when you push the magnetic field into it. When you have 20 turns, more rate of cutting. Definitely right. 2, 3 wire cutting, now more wires are cutting the flux. So number 3 is the number of turns of the solenoid. Okay, so all this is given at page 76. Page 76 you can refer about Faraday law and the expansion of the Faraday law, how the rate of cutting this can be increased. Then number 1 I did again. Moving the magnet in the or solenoid at a higher speed. B for speed, velocity. Increasing the number of turns. You use more turns. More turns, more cutting of rate of cutting. More rate of cutting, so greater the magnitude. And number 3, increasing the strength of magnetic field. That means you use stronger magnet. When you use stronger magnet, how you can increase the stronger? Of course, you can use a stronger magnet by material like molybdenum. We have a steel magnet, we have a molybdenum magnet. Molybdenum magnet, more stronger, a different material. Or you can use 2 bar magnet or 3 bar magnet together and push through it. So you have more flux, greater the rate of cutting. So this is what I'm trying to convey to you today's lessons. Okay, 2 things. One's about direction of induced current. Another one, magnitude of induced current. Okay, so direction of induced current we discussed. Now magnitude of induced current, Faraday law. Okay, since they say 3 things here, alright, speed, the number of strength of magnetic field, and the number of turns. So these 3 are variables. So there is always a chance for them to ask question in paper 3. Alright, how you change the speed to induce the greater magnitude of current, or how you change the magnet, or how you change the number of turns. Maybe I might give 1 or 2 questions regarding this from your paper 3 for you to try how you outline an experiment to verify these parameters, verify these parameters or the variables in order to prove that magnitude of induced current is increased. Okay, so probably after this lesson I might give you some exercise, maybe some passive questions and some Coulomb questions regarding the subtopics of induction, electromagnetic induction. So please try those questions. I might give you the answer maybe later, and then we will discuss any questions that you have doubt there. Right? So with that I end today's lesson. So hope please review back my clip, and then please try to get understand. And things you have to remember. One, you have to remember the definition of Faraday law. The other, you have to remember the definition of Lenz law. Do not confuse. One for direction, one for magnitude. Alright. So with that I end today's lesson. So please revise your work, and thank you very much for your time, and have a pleasant day. We will meet soon. Okay. Thank you very much.